In this lesson, we're going to start by reviewing the laws of exponents. Then we're going to be multiplying polynomials. We'll practice using the distributive property, we will FOIL, we will review the difference of two squares, and we'll practice finding the product of two functions. We're going to start by reviewing the laws of exponents. These laws of exponents are very important. They come up over and over again in mathematics. We'll start with the product rule. When you're multiplying two quantities that have the same variable base, x in this case, the product rule tells us that we can just keep the base, x, and then for our exponent, we just add these two exponents. So we'll take 3 plus 4. And that will leave us with x to the 7th. It's nice to see the reasoning behind this rule. Let's quickly take a look at what we're actually doing here. X to the 3rd means that we're multiplying x by itself 3 times. So x times x times x. X to the 4th means x times itself 4 times. So when we take x to the 3rd times x to the 4th, we end up with x times itself 7 times, or in other words, x to the 7th. Let's try a little bit more complicated problem here. I'm going to start by rewriting this. 3w to the 5th z cubed simply means 3 times w to the 5th times z cubed. And then we're multiplying by 6w to the 7th z, which means 6 times w to the 7th times z. These parentheses here just mean multiplication. If we add this multiplication symbol here, we don't need the parentheses. Now, when you're multiplying, we always multiply like pieces. So let's put the like pieces next to each other. 3 and 6 are just numbers, so those are like pieces. So I've written the 3 times the 6 right next to each other. W to the 5th and W to the 7th are like pieces, so let's write those pieces next to each other. And then the z cubed and the z are like pieces, so let's write the z's next to each other. Now, remember the commutative property tells us that when you're multiplying, you can reorganize the pieces in any order, and that's just what I've done here. Now let's go ahead and multiply the like pieces. 3 times 6 gives us 18. When we're multiplying w to the 5th times w to the 7th, remember this product rule up here. When you multiply two quantities with the same base, we keep the base and add the exponents. So 5 plus 7 will give us 12. And then when we're multiplying the z's, again, we keep the base, which is the z, and we add the exponents. This implied exponent is a 1, so we'll be adding 3 plus 1 to give us z to the 4th. So those were examples of the product rule. Now let's review the quotient rule. The quotient rule says that when you're dividing two quantities with the same base, you keep the base, which is the x, and then to find the exponent here, we just take the exponent in the numerator minus the exponent in the denominator, 5 minus 3. And that will leave us with x squared. Again, we can write out the x's like we did here to verify that this rule does work. For example, to represent x to the 5th, we take x times itself 5 times, and then we're dividing by x cubed. X cubed can be written as x times itself 3 times. Now we can do some canceling. We can cancel this x in the numerator with this x in the denominator. We can cancel this x and this x, and this x and this x, and that leaves us with x squared, which is exactly what we had for our answer here. Now let's use the quotient rule to try a problem that's a little bit more complicated. Remember, with multiplication, you multiply the like pieces. So we multiplied the numbers, we multiplied the w's, and we multiplied the z's. Same with division. We divide like pieces. So the 27 and 12 are just numbers, so we can divide those. We can reduce 27 twelfths if we divide the numerator and the denominator by 3. 27 divided by 3 gives us 9, and 12 divided by 3 gives us 4. So we've reduced 27 twelfths to 9 fourths. Now the a's are like quantities, so we want to divide the a's. And we're going to use the quotient rule here. When you divide two quantities that have the same base, which is a in this case, we keep the base, a, and then we subtract the exponent. So we're going to take 5 minus 2 to give us 3. Similarly, the b's are like quantities, so we're going to divide the b's. And when we divide two quantities with the same base, we use the quotient rule. We keep the base, which is b, and we subtract the exponent. So we're going to take 3 minus this exponent, which is a 1. 3 minus 1 gives us 2. So our final answer would look like this, or if we prefer, we could write our final answer like this. Next, let's review the zero exponent rule. The zero exponent rule says anytime you raise a quantity to the zero exponent, you get 1. So 4 to the 0 is 1. The quantity 5x raised to the 0 is 1. Notice here the zero exponent applies to this entire quantity. So if you're raising an entire quantity to 0, you get 1. If there's no parentheses, then you automatically assume that the exponent only applies to what it's directly next to. So in this case, the 0 only applies to the x. So I'm going to rewrite this, just separating the pieces as 5 times x to the 0. So let's start by bringing down the 5, and then x to the 0 will give us 1. So we're left with 5 times 1, which gives us 5. If you're curious about the reasoning behind why raising a number to the 0 exponent gives you 1, feel free to ask. I'm happy to explain it to you. Next, we're going to discuss the power rule. The power rule says that when you have an exponent raised to an exponent, to simplify it, you just keep your base, which is x in this case, and then our new exponent is the product of these two exponents. So we're going to take 2 times 4. And that will leave us with x to the 8th. Let's try one more. If we're taking t cubed and raising it to the 7th, we're raising an exponent to an exponent. So we use the power rule. We keep the base, which is a t, and then we multiply the exponents. So we'll take 3 times 7, which will leave us with t to the 21st. Next, we're going to discuss the negative exponent rule. Before we get into the negative exponent rule, I want to quickly discuss negative exponents. So when mathematicians were defining the language of mathematics, they decided that x cubed means that you're multiplying x by itself 3 times. But then mathematicians had to decide, what if you have a negative exponent? For example, what if you have x to the negative 3? What does that mean? Well, x cubed means x times itself 3 times, but it doesn't make sense to say that x to the negative 3 means x times itself negative 3 times. That sentence doesn't really make sense. So mathematicians agreed that since x cubed means x times itself 3 times, and since 3 and negative 3 are opposites, x to the negative 3 would simply mean that we're dividing by x 3 times, and that would leave us with 1 over x cubed. Now in mathematics, we prefer not to leave our final answers with negative exponents. So if you have a statement like this, x to the negative 3, we always rewrite it in this form with positive exponents. Most people just memorize the rule that if you have a negative exponent in the numerator, you can just bring this quantity down to the denominator, and that makes the exponent positive. So now let's discuss this negative exponent rule. So here we see a negative exponent. We don't like to have negative exponents. So to rewrite this, we just pick this up and move it to the denominator. And when we do that, our exponent becomes positive. So that will leave us with 1 over x to the positive 4th. Now, if your negative exponent is in the numerator, you just bring it to the denominator and your exponent becomes positive. It works in the reverse direction as well. If your negative exponent is in the denominator, you can just pick it up and move it to the numerator, and then your exponent will become positive. So if we pick up this quantity and move it to the numerator, that will leave us with x to the positive 5th in the numerator. Now let's take a look at this. Here, since there are no parentheses, we assume that this exponent applies only to what it's directly next to. So this exponent is only being applied to the x. So the 4 does not have a negative exponent. So we're going to leave the 4 where it is. But we have x raised to the negative 6, and we don't like to have negative exponents. So to fix that, let's pick up this x to the negative 6 and move it to the denominator, and that will make the exponent positive. So that leaves us with x to the positive 6 in the denominator. Let's take a look at our last 2 laws of exponents. The product to a power rule says that when you have products being raised to an exponent, we can apply this exponent to each of the quantities being multiplied inside the parentheses. So we can rewrite this as x to the 10th times y to the 10th. Let's try one more. So again, when you have multiple pieces being multiplied inside of parentheses, You can apply your exponent to each of those pieces being multiplied. Be careful here, we have 3 pieces being multiplied inside of the parentheses. This is -6 times r to the 5th times s. So we have to apply this exponent to each of those 3 pieces. So we'll apply the 2 to the -6. That will give us -6 squared. Then we'll apply the 2 to the r to the 5th to get r to the 5th squared. And then we'll apply the 2 to the s to get s squared. Now let's simplify. -6 squared is the same as -6 times -6, which gives us a positive 36. When you raise an exponent to an exponent, you multiply. So this would leave us with r to the 5 times 2, or in other words, r to the 10th. And then we'll bring down the s squared. Lastly, there's the quotient to a power rule. This says that if you have pieces being divided inside of parentheses, you can apply your outside exponent to each piece being divided inside the parentheses. In other words, we can apply the 3 to the x to give us x cubed, and then we can apply the 3 to the y to give us y cubed. For this example, we're going to be combining some of the exponent laws that we just learned. Remember, when you have pieces being multiplied or divided inside of parentheses, you can apply your exponent to each of those pieces. Let's apply the 4 to each of the pieces being multiplied in the numerator. So we'll apply the 4 to the 2 to give us 2 to the 4th. Then we'll apply the 4 to the x to the 6th to give us x to the 6th to the 4th. Then we'll apply the 4 to each of the pieces being multiplied in the denominator. We'll apply the 4 to the 3 to give us 3 to the 4th. And then we'll apply the 4 to the y to the 5th to give us y to the 5th to the 4th. Now we just need to simplify. 2 to the 4th gives us 16. X to the 6th to the 4th, we're raising an exponent to an exponent, so we multiply those exponents. 6 times 4 gives us 24, so we have x to the 24. And then in the denominator, 3 to the 4th gives us 81. And then here we multiply the exponents, 5 times 4 to give us 20, so we'll have y to the 20th. Now you want to check to see if the fraction 16 over 81 can be simplified, but it cannot. So this is our final fully simplified answer. Now we're going to use those laws of exponents as we work through several examples. For this first problem here, remember when we multiply quantities, we multiply like quantities. The commutative property tells us that when we're multiplying quantities, we can reorganize those quantities in any order. So I'm going to put the like quantities next to each other. The 12/5 and the 15/4 are both numbers, so I'm going to put those numbers next to each other. Similarly, the x squared and the x to the 4th are like quantities, so I'm going to write those quantities next to each other. And the y's are like quantities, so I'm going to write the y's next to each other. Now we can start by just multiplying these two numbers. And when we multiply fractions, we just multiply the numerators and multiply the denominators. 12 times 15 gives us 180. And 5 times 4 gives us 20. And when we multiply the x's here, we'll use the product rule. The product rule tells us when you're multiplying two quantities with the same base, we keep the base, which is x, and we add the exponents. So we'll add 2 plus 4. And again, we'll use the product rule with the y's. When we're multiplying y times y cubed, we keep the base, which is y, and we add the exponents. So we'll take 1 plus 3. Then we can simplify. 180 divided by 20 gives us 9. This will simplify to x to the 6th, and this will simplify to y to the 4th. Next, we're going to take a look at an example where we use the distributive property. Notice the distributive property is only used if you have addition or subtraction symbols inside your parentheses. If you don't see addition or subtraction symbols inside your parentheses, then you will never use the distributive property. So to use the distributive property, we're going to take this -3a squared b and distribute or multiply it by each of these terms inside the parentheses. Let's start by taking -3a squared b and multiplying it by 8a to the 5th. And I'm just going to start by writing that out. So we're taking -3a squared b times 8a to the 5th. Then we'll multiply the -3a squared b times the 3ab, and I'm going to write that out. So we're taking -3a squared b times 3ab. And lastly, we're going to take the negative 3a squared b and multiply it by negative b cubed. So to write that out, we're taking negative 3a squared b times negative b cubed. Now let's go ahead and simplify. Let's start by looking at this quantity in orange, and we're going to use the same process that we used up here. When you're multiplying, you just multiply like quantities. So let's multiply the negative 3 times 8 to get negative 24. Then let's multiply the a's. When we multiply a squared times a to the 5th, we add the exponents. So that will give us a to the 7th. And then there's only one b here. There's nothing to multiply the b by, so we can just bring down the b. Now let's work with this quantity in blue here. We always multiply like quantities. So let's take the negative 3 times the 3 to get negative 9. Then let's multiply the a's. When we multiply a squared times a, we keep the base, which is the a, and we add the exponents. So 2 plus 1 will give us a cubed. And then let's multiply the b's. When we multiply b times b, we keep the base and add the exponents. So we'll be taking 1 plus 1 to get 2. Now let's simplify this expression in purple here. To start, negative b cubed, we could think of this as negative 1 times b cubed. So if we take the negative 3 times the negative 1, that'll give us a positive 3. Then let's see here, there's nothing to multiply this a squared by, so we'll just bring down the a squared. And then if we multiply b times b cubed, we keep the base, which is b, and if we add the exponents, 1 plus 3 will give us 4. Now, can we simplify this any further? We cannot. These are each terms. Terms are quantities separated by addition or subtraction symbols. And you can only add or subtract terms if they're like terms. Quantities are like terms if they have the same exact variable base. Here the variable base is a to the 7th b. Here the variable base is different. It's a cubed b squared. And here the variable base is different. It's a squared b to the 4th. So all three of these terms have different variable bases. So they're not like terms, so they cannot be combined. So this is our final fully simplified answer. Next, we're going to multiply binomials. Bi means two. You can think of a bicycle that has two wheels. And a binomial is something like this, where it has two terms, 1, 2. Here we're taking this binomial and multiplying it by this binomial. When we're multiplying two binomials, we FOIL. The F in FOIL stands for first. So that tells us we multiply the first term in each parenthesis. So we're going to take the 3m times the m. 3m times m will give us 3m squared. The O in FOIL stands for the outer, and so we multiply the outer terms in each parenthesis. So we're going to multiply the 3m times the 2n. 3m times 2n will give us a positive 6mn. The I in FOIL stands for inner, and that tells us to multiply the inner two terms. So we're going to take negative 5n times m. Negative 5n times m will give us negative 5nm. Now, typically when we're writing expressions in mathematics, we put the variables in alphabetical order. So m comes before n in the alphabet, so I'm going to write this as negative 5mn. And finally, the L in FOIL stands for last, and that tells us to multiply the last quantity in each parenthesis. So we're going to take the negative 5n times the 2n. Let's see, negative 5 times 2 will give us negative 10, and n times n will give us n squared. Now we want to simplify. These two middle terms have the same variable base, mn. So they're like terms, so we can combine them. And when we combine like terms, we keep the variable base, which is mn, and then we add or subtract the coefficients. So 6 minus 5 will give us 1. If your coefficient is a 1, you don't have to write it. Now I'm just going to bring down the other terms. 3m squared. And since 6 minus 5 gave us positive 1, I'm going to write plus, and then we'll bring down the negative 10n squared. And this is our final answer. Now, a common confusion that comes up is students will see an expression like this and they will try to FOIL. You only FOIL if you see addition or subtraction symbols in both of your parentheses. Here, while we have two parentheses, we don't see addition or subtraction symbols inside those parentheses, so we never would FOIL. Let's try another example. Here, notice we have two sets of parentheses. We have an addition symbol in this parenthesis and a subtraction symbol in that parenthesis. So this is a case where we want to FOIL. So the F in FOIL stands for first. So I'm going to multiply the 3/2 y times the 4/3 y. And I'm just going to start by writing just that. 3/2 y times 4/3 y. Then the O in FOIL stands for the outer. So I'm going to take 3/2 y times -1. 3/2 y times -1 will give us -3/2 y. The I in FOIL stands for inner, so I'm going to multiply the 4 times the 4/3 y. And then the L in FOIL stands for last, so I'm going to multiply the 4 times the -1. And 4 times -1 will give us -4. Now we just want to simplify. To simplify this expression in pink, remember when you're multiplying, you multiply the like pieces. So we can multiply the fractions 3/2 times 4/3. You can do that by hand or using your calculator. Either way, 3/2 times 4/3 will give us 2. And then we multiply the y's. Y times y will give us y squared. Then I'm just going to bring down the -3/2 y. Then here, to simplify this expression in purple, remember when you're multiplying, just multiply the like quantities. So multiply the numbers, and you could do this by hand or on your calculator. Either way, 4 times 4/3 will give us a positive 16/3. And then we'll bring down the y. And then let's bring down the -4. Now we have some like terms here. Both of these terms here have the same variable base, y. So these are like terms. So to combine these, we keep the base, which is a y, and then when we're combining like terms, we just add the coefficients. You can do this by hand by getting a common denominator, or just pull out your calculator, and if you take -3/2 plus 16/3, you'll get a positive 23/6. And then let's bring down the other pieces, the -4 and the 2y squared. Now we've simplified as much as we can. None of these are like terms, so we've arrived at our final answer. Let's take a look at another example. Now this is a type of problem that is very often solved incorrectly. So before I show you the correct way to solve this problem, I'm going to show you the very common wrong way to solve this problem. A lot of people are tempted to try to distribute exponents. So people will take this 2 and try to distribute it to the x to get x squared. And then they'll take the 2 and distribute it to the 8 to get 8 squared. And then they might simplify this to x squared minus 64. The key here is that exponents don't distribute over addition or subtraction. You can't use the distributive property with exponents. So do not try to distribute an exponent in a situation like this. The correct way to solve this problem is to first rewrite this. The quantity x minus 8 squared can be rewritten as the quantity x minus 8 times the quantity x minus 8. Now we're going to want to FOIL. So to FOIL, we start with the first. We'll take x times x, which will give us x squared. Then we'll do the outer. We'll take x times -8 to get -8x. Then we'll do the inner. We'll take -8 times x to get another -8x. And then we'll do the last. We'll take -8 times -8 to get positive 64. Now these are like terms, so they can be combined. -8x minus 8x will give us -16x. And then we'll bring down the x squared and the positive 64. And that gives us our final answer. Now we're going to be multiplying larger polynomials. But first I want to discuss what we're actually doing when we FOIL. When we FOIL, we multiply the first, so we take x times x. Then we multiply the outer, so we take x times 2. What are we actually doing here? Well, we're taking this term and distributing it to each term in this second set of parentheses. Then with FOILing, the next step is to multiply the inner. So we multiply the 4 times the x, and then we do the last. So we multiply the 4 times the 2. So what are we doing here? Well, we're taking this 4 and we're distributing it to each of these quantities in this second parenthesis. So the FOIL acronym is really just a trick to guide you into distributing. The FOIL acronym guides you into distributing this x to each term in this second parenthesis, and then the FOIL acronym guides you into distributing this 4 to each term in this second parenthesis. Now you can only use the FOIL acronym when you're multiplying binomials. So two parentheses that each have two terms inside their parentheses. So this is not a binomial, and neither are these. So we can't use the FOIL acronym here, but we can just use the basic distributive property. So the distributive property tells us to take this term here and to distribute it to each of the terms in this second set of parentheses. So let's start by taking the 2y and distributing it to the y squared. 2y times y squared will give us 2y cubed. We just added the exponents, 1 plus 2 to give us 3. Then we'll take this 2y and distribute it to the 6y. When we multiply 2y times 6y, we'll take 2 times 6 to get a positive 12, and y times y will give us y squared. Remember, when you're multiplying, you just multiply like quantities. So we multiply the 2 and the 6 and the y and the y. Then let's distribute the 2y to the negative 8. And 2y times negative 8 will give us negative 16y. Okay, so we've taken this first term and distributed it to each of the quantities in that second parentheses. Next, we're going to take this term and distribute it to each of the quantities in the second parentheses. So first we'll take negative 4 times y squared to get negative 4y squared. Now we're going to end up with a whole bunch of terms here, so I recommend that you line up like terms. So this is going to give us negative 4y squared, so I'm going to write the negative 4y squared directly below the 12y squared. Then let's multiply the negative 4 times the 6y, and that will give us negative 24y. And notice I've aligned the y terms here. And then we're going to take the negative 4 and distribute it to the negative 8. Negative 4 times negative 8 will give us positive 32. Now we want to simplify by combining like terms. There's no other y cubed terms, so we'll just bring down the 2y cubed. These are like terms, so we can combine them. 12y squared minus 4y squared will give us a positive 8y squared. Negative 16y minus 24y will give us negative 40y. And then we'll bring down the positive 32. Let's try this example. To start, we'll take this term and distribute it to each of the terms in that second set of parentheses. Z squared times 2z squared will give us 2z to the 4th. We added the exponents. 2 plus 2 gives us 4. Z squared times z will give us a positive z cubed. We add the exponents. And then let's take the z squared and distribute it to the 6. Z squared times 6 will give us a positive 6z squared. Then let's take this second term and distribute it to each of these three terms here. If we take negative 3z and distribute it to the 2z squared, let's see, we'll multiply the negative 3 times the 2 to get negative 6. And the z times the z squared will give us z cubed. Notice I've aligned the z cubes. Then let's take this negative 3z and distribute it to the z. Negative 3z times z will give us a negative 3z squared. And then let's take the negative 3z and distribute it to the 6. And negative 3z times 6 will give us negative 18z. Finally, let's take this 2 and distribute it to each of these three terms. If we take 2 times 2z squared, that'll give us a positive 4z squared. And I'm going to put that directly underneath our other z squares. Then let's take the 2 and distribute it to the z. 2 times z will give us a positive 2z. And notice I put that directly underneath this z. And then let's take the 2 times the 6, and 2 times 6 will give us a positive 12. Now we want to combine like terms. And since we've lined up all of the like terms, this process will be a little bit easier. So there's no other z to the 4ths, so we'll just bring down the 2z to the 4th. 1z cubed minus 6z cubed will give us negative 5z cubed. Let's see. When we're adding these z squared like terms, 6 minus 3 will give us 3, plus 4 will give us a positive 7z squared. Negative 18z plus 2z will give us negative 16z, and then we'll bring down the positive 12. And this is our final fully simplified answer. Next, we're going to look at a special case where we can use the difference of two squares formula. Notice these two examples. What's inside these parentheses looks identical. The only difference is that this parenthesis has a plus sign and this parenthesis has a minus sign. Same thing here. What's inside these two parentheses is identical. The only difference is that we have a subtraction symbol in this parenthesis and an addition symbol in this parenthesis. When your two parentheses look identical, but one has a plus and one has a minus, you can always FOIL, but there's another strategy called the difference of two squares formula that we can use. Let's try both strategies. Let's first FOIL here. Now, whenever you have this situation where what's inside your parentheses looks identical, but one has a plus and one has a minus, when you FOIL, the middle terms always cancel out. And we're just left with x squared minus 16. So we FOILed here, and FOILing always works when you're multiplying two binomials. But if your binomials look identical, but one has a plus and one has a minus, instead of FOILing, you could use the difference of two squares formula. When you're multiplying two quantities that look identical, but one has a plus and one has a minus, the shortcut is you just need to take this first term and square it to get a squared, and then take this second term and square it to get b squared. And then we always put a subtraction sign in the middle. That's why it's called the difference of two squares formula, because you're taking the difference or subtraction of two squares. Let's try using the difference of two squares formula to solve this problem here. So if we use the difference of two squares formula, that formula tells us just take this first quantity and square it. That gives us x squared. Then take the second quantity and square it, which gives us 4 squared. And then we'd always put a subtraction sign in the middle. And this would simplify to x squared minus 16, which is the same answer we got using the FOIL method. Now for this example here, we could of course FOIL and we'd get the correct answer. But since we have that special case where we have two parentheses that look identical, the only difference is that one has a plus and one has a minus, we could use the difference of two squares formula. And that's what I'm going to do here. So when we use the difference of two squares formula, we start by taking this first quantity, 5x, and squaring it. Make sure to put parentheses around it so that we square that whole quantity. And then we take the 2 and square it. And then we always put a subtraction sign in the middle. Now we simplify. Now remember, the product to a power rule says that when you're multiplying two quantities inside of a parentheses, you can apply your exponent to each of the quantities being multiplied. So we'll apply the 2 to the 5 to give us 5 squared, or 25, and then we'll apply the 2 to the x to get x squared. Then we'll bring down our negative, and 2 squared gives us 4. And this is our final answer. We would get this same answer if we were to FOIL. Notice with the difference of two squares formula, you should always have a subtraction symbol in your final answer between your two terms. Let's take a look at one last example problem. So this is function notation here. This means the same exact thing as f of x times g of x. So anytime you see this notation here, you can rewrite it as f of x times g of x. So let's do that here. So here we see f times g of x. Let's rewrite this as f of x times g of x. Now let's look at the given information. We're told that f of x is equal to x plus 5. So let's go ahead and replace f of x with what it's equal to, which is x plus 5. And then if we look back up at the given information, we're told that g of x is equal to 2x plus 1. So let's replace g of x with what it's equal to, 2x plus 1. Now we've got a very familiar problem where we want to FOIL. let's try one last problem. Now this problem can be solved in two different ways. Method 1 is similar to what we just did in Part A. Part A, remember, we started by rewriting the problem in an equivalent form. Let's do that here. Here we have f times g of 3. The only difference between these two problems is that instead of having an x, we have a 3 here. So this can be rewritten as f of 3 times g of 3. Now, let's remember, what does f of 3 mean? F of 3 means go look at your function f of x, and wherever you see x, you replace it with 3. So that will give us 3 plus 5. Similarly, g of 3 means go look at your function g, and wherever we see x, we replace it with 3. So that will give us 2 times 3 plus 1. Then let's simplify. 3 plus 5 simplifies to 8. And 2 times 3 plus 1 simplifies to 7. And 8 times 7 gives us 56. Can you think of another method we could have used to solve Part B? Well, let's consider our answer for Part A. Part A asked us to find f times g of x, and we did. We found that f times g of x was equal to this quantity here. Part B asks us to find f times g of 3. Again, the only difference between this statement and this statement is that here we have an x and here we have a 3. So to solve this, we're just going to plug 3 in for x here. That will give us 2 times 3 squared plus 11 times 3 plus 5. And if we simplify, this will leave us with 2 times 9 plus 33 plus 5, which will leave us with 18 plus 33 plus 5, which will give us 56. So notice these are just two different approaches that both give us the same answer.